Okay, number 3. Which is larger, E naught of the cell?
Is it B?
It's B, yeah. It's B.
Why?
Well, because this is reference to like absolute zero, so this is going to be a higher voltage. It's just pushing the electrons backwards. And so it's B is the correct answer. For number 2, though, number 2 has a different reference. Number 2 has the arbitrary zero. And so which is the larger oxidation potential is, what would you say, Tweet? Number 2.
A.
A is correct. You got it. All right, any other questions?
For number 4, can you give us the values to solve for it?
Oh yeah, I gave you the redox chart, you know, the one out of the book. And so you'll have all the values for it. Number 1. No, it doesn't mean the battery is dead. If it has an oxidation potential of 0 volts, we don't know what the reduction potential is. If the reduction potential is 0 volts, then the battery's dead. But if the reduction potential is greater than 0 volts, then the battery is operational. We see that here. Actually, I don't want to go there. Both the reduction potential of H plus is 0 volts, and the oxidation potential of H2 is 0 volts. And so H2 has a 0 volt oxidation potential, therefore we need a reduction potential greater than 0 volts. And so H2 will react with any of these species here, will create a positive voltage. So just because the oxidation potential is 0 doesn't mean the other potential has to be 0. And the cell potential is the oxidation potential plus the reduction potential, or the anode potential plus the cathode potential. All right, other questions? What's that? No, we can't. We can't because, you know, I have mixed reservations because some people want to treat this like a real mock exam, and they don't want the answers, actually. They want to try to figure out the answers themselves. Otherwise, it'd just be like more examples. I already did examples, some of this stuff. And the book does examples, so it's just more examples. And so, but I'll cover whatever. I mean, if there's a question about a specific problem, I'll cover that. You know, including up to the entire exam if need be. But was there any other question in this?
6 and 7.
6. Cell potential less than 0 volts means the reaction is non-spontaneous. True or false? It's true. It means the reverse reaction. It's trying to do the reverse reaction because it's trying to force the electrons backwards. And therefore the reverse reaction is spontaneous. But the reaction, you know, this is relative because it depends on how we write it, because we write the anode on the left, the cathode on the right. And the anode should be supplying the electrons to the cathode. The electrons should be moving left to right. But when we get a negative voltage like this, it means it wants to go backwards, so we misassign them. 7. A reduction potential less than 0 volts means the reverse reaction is spontaneous. Is that true or false? Well, there are two different reference points here. You know, when we're dealing with reduction potential, just a negative, like this. A negative 10 degrees Celsius means that everybody moves backwards, you know? Like, for example, positive 10 degrees Celsius means everybody moves forward. When you go negative, that means you have to walk backwards. Is that true or false? That's false, right? What does negative 10 degrees C mean relative to positive 10 degrees C? It just means it's 20 degrees colder. That's all. And the same thing with this. What does a negative reduction potential mean? It just means it's weaker than it means it's weaker than H plus. These are all reduction potentials. So H plus is an oxidizing agent. That means it's a weaker oxidizing agent than H plus. So for example, lead 2 is a weaker oxidizing agent than H plus because its reduction potential is less than H plus is. Just because it's negative does not mean that lead 2, you know, and this is why you have to get the vocabulary right. You have to just drill this in your head. You know, reduction potentials are for oxidizing agents. And so that doesn't mean that lead 2 all of a sudden is a reducing agent. No, it just means it's weaker than H plus. That's because individual half potentials, these are called half potentials. Half potentials have an arbitrary reference. The arbitrary reference is this pink one here, the red one here. Whereas cell potentials have an absolute reference because if you have a 0 cell potential, that means that there's no voltage, your battery is dead. If you have a 0 reduction potential, that means there's no reduction. H plus is not capable of oxidizing anything? No, it's wrong. H plus is a good oxidizer. H plus can oxidize all these metals, lead, tin, iron, zinc. H plus will attack those and oxidize all of them. And so you have to get it clear in your head, you know, the difference between the 3 potentials we talked about. Oxidation potential, reduction potential, and cell potential. Oxidation and reduction potentials have arbitrary zeros. Cell potentials, those arbitrary zeros cancel each other out. And we have an absolute zero as a reference. Okay, other questions? So zinc plus copper 2 plus, redox reaction. Circle all suitable cathodes. So what goes on the right? The cathode goes on the right. Also, the oxidizer or the reducer goes on the right. At the cathode, the oxidizer or the reducer is found at the cathode. Something's going to pull the electrons from left to right. And so on the right side, what's pulling the electron? The zinc metal or the copper 2? For number 11. what's pulling the electrons left to right? So something's pulling the electrons through the wire. Is it the zinc metal or the copper tube? It's the copper tube. Copper tube wants electrons, right? Zinc metal doesn't. And so at the cathode, we have copper 2. And at the cathode reaction is just going to be copper 2. Something has to feed the electrons to copper 2. What feeds the electrons to copper 2 is called the electrode. Since this is where reduction occurs, this is called the cathode over here. And so, you know, the cathode is, well, what's pulling the electrons? Well, copper 2 wants those electrons. And so we need some kind of electrical conductor that will give the electrons to copper 2 ions so that they could deposit copper metal on the surface of the electrode. And so what electrode materials are suitable? You built this in the lab. I don't know if you remember it, but you know, two of these should be pretty easy because you did this, and I think you did it. Some people didn't because they took off ASAP. Yeah, copper and graphite, you know. Yeah, what about platinum? So copper works, graphite works. So both of these should have worked. Did they generate a voltage, either one? Copper and graphite? Yeah. How about zinc? Would zinc be good? For the cathode. Would zinc be good for the cathode? No, it would be very bad for the cathode. The reason zinc would be very bad is what's going to pull the electrons through the wire. So copper 2 has no reason to pull electrons through the wire because if it can just take them straight from zinc, then no problem. We have to keep the zinc separate. Otherwise, the copper 2 will attack the zinc directly. We want it to attack the zinc indirectly. So the zinc is going to be our anode, not our cathode. Zinc we want as our anode. We can use PT. PT is fine, but it's too expensive for us, so we didn't do it, PT. PT is very common, the most common inert electrode. Okay, what else is there? Magnesium. What do you think about magnesium? Well, let's take a look at our chart. Well, here's zinc. Zinc, we say that zinc has an oxidation potential. The reverse reaction is oxidation. So zinc can be oxidized as Zn2 plus 2 electrons. Zinc has an oxidation potential of plus 0.763 volts. That's kind of high, right? What does that mean? That means zinc is easy to oxidize. Right? It has a high oxidation potential, easy to oxidize. Plus 0.763 volts. We're looking at it backwards. How about magnesium? Well, if we reverse this, we have the oxidation potential for magnesium. If we look at the oxidation potential for magnesium, because we're going backwards here, it's plus 2.3 volts. So what has a higher oxidation potential, magnesium or zinc? Magnesium. Magnesium has a very high oxidation potential. So if we use magnesium for our cathode, there's no way to ever pull electrons from zinc. It would just take them straight from the magnesium. If it takes them straight from the magnesium, there's no electrons that are going to flow through this wire. Right? And so that would be called a reactive electrode, and we wouldn't generate any electricity if we use that. And so magnesium is no good. So just platinum, copper, and graphite are good. Okay, any other questions from this? 13, as E of the cell decreases, delta G does what? Delta G is going to increase. Because delta G is just equal to minus N, or Z, minus Z F E of the cell. So as E of the cell gets smaller, delta G is going to get more positive, bigger. Does that make sense? Because we say, you know, positive delta G is non-spontaneous and negative delta G is spontaneous. Okay, any other questions? 15. Well, Tammy, you're gonna get all of them. Did you guys look at these? And did you guys look at them? You really want me to go through them all? Or do you want to try it as a practice test? We'll go through, let's see, when a battery has consumed 50% of the reactants, the voltage should be 50% of its original voltage. True or false? No, this is different. This is a different one. Different kind of story. This is your understanding of the Nernst equation. If you don't know, you know, sometimes when you don't know, you should just do a calculation and see. And so you make up a calculation and see what happens if you have 50% reaction. So we could just make up a calculation. Let's just do this one. The Zn solid plus copper 2 plus yields Zn2 plus copper solid. This is easy enough. We'll start off under standard conditions. Under standard conditions, what are the concentrations? Zinc is a solid, so this is 1 molar, and copper is a solid. So it's 1 molar, 1 molar. The change is we want minus 50%, right? We want to lose 50%. So what's half of 1 molar? This is easy, 0.5 molar. So we pick easy numbers to make our life easier. And so after 50% reaction, you know, we're going to end up with, okay, 0.5 and 1.5 molar. And so we can compare the cell potential. The cell potential here, well, this is under standard conditions, so we just add up the two half reactions. We have zinc goes to Zn solid, so we're going from Zn to Zn AQ, Zn2 plus AQ, Zn solid. What do we call that? The oxidation potential or the reduction potential? This is the oxidation potential. Where does oxidation occur? At the anode. And so we could call this the Zn2 plus couple, or the oxidation potential, or the anode potential. And then we just add that to the copper 2 plus goes to copper. Copper 2 plus goes to copper, which we call the reduction potential or the cathode. So first, let's look for Zn goes to Zn2 plus. Here it is at the bottom. Zn goes to Zn2 plus, so we have to reverse this. If we reverse this, we change the sign. And so Zn goes to Zn2 plus, this is going to be plus 0.763 volts. So high potential. That means there's a high potential for zinc becoming oxidized. And then we go for copper 2 to copper metal. We're just going to use this as is because that's the right, copper 2 to copper metal, plus 0.340 volts. And so this is going to be plus 0.340 volts, which is going to give us 1.1 volts, 1.1 ... volts. Right? So under standard conditions, it's at 1 molar, everything. Now, if I have 50% reaction, is the voltage going to be 0.55 volts? Well, let's see. Because under non-standard, is this standard or non-standard condition? Non-standard. And non-standard, we're going to use what equation? We're going to use the Nernst equation. E of the cell is equal to E naught of the cell minus 0.0592 volts over Z, or N, log base 10 of Q. So E naught of the cell is, we just calculated that, this 1.1 ... volts minus 0.0592 divided by Z. What is Z? How many electrons are transferred in the balanced chemical reaction? 2, right? We can see Zn produces 2 electrons. Copper 2 consumes 2 electrons, so 2, right? Log of Q. Q is the activity of the products over the activity of the reactants. Activity of pure solids is 1, so we ignore that. And so this is going to be the concentration of Zn2 plus divided by the concentration of Cu2 plus. The Zn2 plus is 1.5 molar, or 1.5. Activities don't have any dimensions, so we don't include that. And the Cu2 plus is 0.5. So calculate what this term is. Does this term come out to minus 0.55? If it does, then we just lost half our voltage. What's your guess, though? Yeah, it changed. It used to be standard, but after half of it's been consumed, is it still standard? No. You know, the voltage is always changing, and standard conditions is just the one snapshot of the voltage. So right at this point, it's standard. Every other point, it's non-standard. .09. All right. Then did we lose half the voltage? No, not even close. So if there's one exception like this, then that statement is false. Is false. So we, even though we didn't know, yeah, maybe not. We just make up a calculation and test it, and it failed. And therefore, we can say it's false. Okay, any other questions on this?
16.
You gave it a shot, right? Well, I guess we're kind of tight with time, so we'll just do it. Doubling the reaction doubles what? If you compare a triple A and a double A is bigger. Yeah, but is a double A, let's say a double A is twice as big as a triple A, does it have twice the voltage? No. So if we double this, double the size of the battery, so we start off with a little battery and make it twice as big, right? It's twice as big of everything. So if you're using twice as much, is it going to be twice the voltage? No. Well, what about if we do it under standard conditions? Will it change E naught of the cell? No. Will it change delta G? Yes. Changes delta G. We'll change delta G naught. Let's say aluminum chloride. Look at aluminum chloride, the delta G naught is minus 628. If I double that, let's say I go from 1 mole of aluminum chloride to 2 moles of aluminum chloride, do I get the same amount of energy? Or different amount of energy? Different. Different. In fact, I get twice the amount of energy. And so energy is extensive like that. Cell potentials aren't, because we're going to divide by, we're normalizing the cell potentials by dividing by Z or N. Delta H, will it double? Let's say I burn 1 mole of methane, and now I decide to burn 2 moles of methane. If I burn 2 moles of methane, will I get twice the amount of energy as burning 1 mole of methane? No? Yes? Or let's say if you put 1 gallon of gas versus 2 gallons of gas, does 2 gallons of gas have twice as much energy as 1 gallon, or a different amount of energy? The same energy? Let's say you're on a diet and you eat 1 cheeseburger versus 2 cheeseburgers. 2 cheeseburgers will have twice as many calories as 1 cheeseburger? Yes. So energy like that, you know, calories or joules, this will double. And so delta H will double. It's just the number of calories when you burn something, or the number of energy. And same thing with delta H naught. Delta S naught, these are all extensive properties. The only intensive ones are A and B. And so you should have circled C, D, E, F, G, and H. Entropy, the same thing with entropy. You know, you can expect double the disorder if you have twice as much, because twice as many particles to get all mixed up. Okay, other questions? Okay, you'll want to work on this, and then somebody asked me, why don't I just post the key or at least the answers to this? But I thought, it's... I don't want to post the key to this, actually. Because, learning, you want the answer. You want to be able to check your answer when you're learning something new. It's important to be able to check your answer. But we have a lot of homework problems. And you could do more homework problems than I assign, and those all have the answers. But once you've done those, then you want to be able to apply things. And applying things, you don't necessarily want to be shown, because you want to think through these, and then I think you'll more effectively remember it. Not only that, you want to gain a certain level of confidence, that you're doing it correctly or not doing it correctly. So that, once you gain a certain level of confidence in the problem solving, then you can see some things. Like on this last test, did you guys notice this one? Practice test for exam 19, number 8. Number 8, I didn't tell you this for number 8, but the answer's not there. And so, are you confident enough to say, okay, the answer's not here. This is the correct answer.
It was 0.0.
Yeah, it's the correct answer is 0.03, not 0.3. It's my mistake. Right. Actually, yeah, if you did compare your notes, we did this and we got the right answer, 0.032 in class. And so since we did that one in class, I was thinking, I'm not going to tell you. And then you'll see, But the same thing happens on any test. If you work through the problem and you're sure you're doing it right, then you can confront me about it, and say, the answer's not there. All right, today what we're going to do is we're going to finish up chapter 20. We don't have too much more left. And then we're going to start 24. We're just going to look at isomers, and that's going to be our lab. And so today we're going to be building isomers. Isomers are different structures for the same chemical formula or the same composition. And so let's power through the rest of this PowerPoint presentation here. Okay, so did we talk about the alkaline cell? Alkaline cell? Yeah. Alkaline cell just has hydroxide in there as the electrolyte. We generate hydroxide here. This is the anode or cathode. This reaction is occurring at the anode or the cathode? Yeah, this one's occurring at the cathode. Jonathan, in the morning class, said there's an easy way of remembering it. And so at the anode, oxidation occurs. I never noticed this. But he said A and O are vowels. At the cathode, yeah, reduction occurs. And C and R are constants, so. Yeah, you're right. That's better. But we have reduction, so this has got to be the cathode. The cathode is where we consume electrons, and here we're consuming electrons. Something's got to pull the electrons through the wire, right? What's pulling the electrons through the wire is the oxidizing agent. And so here are the electrons. And so that's going to be in the center here. We have in an alkaline cell, we have hydroxide present. And the purpose of the hydroxide is for the anode. At the anode, oxidation occurs. So they didn't put it, maybe they did put it there. Maybe they didn't. No, they didn't. They left it off. Oh, here, no, they said it here. Oxidation reaction can be thought of in 2 steps. Okay, so first we generate the electrons by oxidizing zinc. Zinc has a fairly high oxidation potential. MnO2 has a fairly high reduction potential. So we want to add these to get a good voltage, a decent voltage. So zinc goes to Zn2 plus, generates the electrons. Now we have hydroxide in the electrolyte, you know, the salt bridge. And that hydroxide can react with zinc in this reaction. This first reaction is a redox. The second reaction is a metathesis. You combine those 2 reactions and we get this redox metathesis deal here. But the thing is, we create solid. And so this is all solids here, one pure liquid and then hydroxide, but the hydroxide ion concentration doesn't change. Hydroxide ion concentration doesn't change because we consume it from the electrolyte, that is the salt bridge, but we replenish it at the cathode. And since that doesn't change, then the voltage stays stable. Here's a car battery. A car battery consists, they don't show it all, but a car battery consists of 6 cells. You can see them here. Each of these caps represents a different cell of the battery. And so they put 6 2-volt cells together like this to create 12 volts. And so here you can see the anode is lead. Lead has a fairly high oxidation potential, meaning it's fairly easy to oxidize. The cathode is actually solid and reactive. And so the cathode, actually, this is lead-4 oxide. Lead-4 oxide doesn't conduct electricity. And so what they do here is they put lead-4 oxide in some kind of checkerboard honeycomb pattern here. And so the lead-4 oxide is going to pull the electrons from the lead. Lead is going to get oxidized to lead-2 plus, and the electrons are going to go from the anode to the cathode here. H2SO4 is our salt bridge there, or electrolyte. This battery, the reaction's not too difficult to reverse. And so when it discharges, it's this pink, electrons flow from anode to cathode. You can recharge this also. You recharge this by putting some kind of power supply or an alternator in here. And what that does is it sucks electrons out from here and forces them back over here. So when it forces them back over here, the lead-2 ions are reconverted back into lead metals, thereby replenishing our lead anode. And when it sucks the electrons out over here, then the lead-4 oxide gets converted into lead, which is then reconverted back to the oxide. The reactions are a little bit complicated here. Here you can see, actually it's not going to lead, it's going to lead-2 sulfate. So here you can see at the cathode we have reduction occurring. So this is pulling the electrons in, form a precipitated PbSO4 which deposits there. At the anode we have the lead going to lead-2 plus. This is also a form of PbSO4. So HSO4 minus is being net consumed. We're consuming it here and we're consuming it here. And so the HSO4 minus concentration is going to be decreasing. And so what that means is sometimes we have to replenish that. Or we recharge it. When we recharge it, then the HSO4 minus concentration will be replenished. Now anyway, the potentials here, the reduction potential, the oxidation potential is not too low. We add those up, we can get roughly 2 volts, 1.5 volts. Okay, to recharge this battery, reverse this net reaction here. This is a silver zinc button battery. And so zinc is a good anode. Zinc is a good anode because it has a high reduction potential or high oxidation potential or low reduction potential and the low oxidation potential. Which one? It has a high oxidation potential. Zinc is a good anode because it has a high oxidation potential. Silver ions, Ag+, are a good oxidizer because it has a high reduction potential. And so the higher the potential, the more likely it is to occur. Well, the silver ions are going to be locked up in crystals of silver oxide, but nonetheless they can gain electrons from silver metal. These crystals of silver oxide are kept in an electrical conducting paste, typically graphite paste. And so you can see the little lines representing the silver oxide. Silver oxide is pulling the electrons. They're going to be pulling the electrons through a wire from the zinc. So this zinc has to be insulated from the steel container. So we've got a steel container here. The steel container will be the cathode, and the oxidizer will be the silver oxide here. And then there's some electrolyte here to maintain space charge neutrality. So the cathode's positive, the anode's negative. Anode's where we generate electrons, so that makes sense it's negative. Cathode's where we consume electrons. So electrons are actually flowing from the negative terminal to the positive terminal here. Anyway, here is the cell diagram for this. When the states are the same, we use a comma. Like, for example, zinc gets oxidized to ZNO. We use a comma because both of these are solid. Sometimes we say what the salt bridge is. And so usually this is double line because we could use any salt for a salt bridge. But for this particular battery, we want to use one specific salt, in this case KOH, saturated. That's our salt bridge there. And then Ag. All right, so this is the reaction here. Yeah. We don't have to worry about this too much, have we? Huh? Oh yeah. These are the little watch batteries, right? Little watch batteries, or they use them for other applications, like car keys and stuff like that. Hearing aids. Yeah, they can get expensive because of the silver. This is nickel cadmium secondary cell. Secondary cells are rechargeable. And so even though this reaction looks complicated, here we probably want our anode as cadmium. Cadmium becomes oxidized. Over here, cathode is going to, the oxidizer here is going to be nickel. Nickel looks like nickel 3, right? Is going to be our oxidizer. Nickel 3 is a bit of an unusual charge for nickel. The most common charge for nickel is nickel 2. But that reaction can be reversed. This is a lithium-ion battery. Lithium-ion battery is totally different. Lithium-ion battery has something called intercalation. Intercalation is this. If we look at graphite, graphite has a bunch of these layers of carbon atoms. And in between two layers typically is nothing. But what you can do is you can force lithium ions in between the layers. That's going to build up a voltage. Because now we've got a lot of positive charge over here. That positive charge wants negative charge, so it's going to draw in electrons because it's too positive over here. When we discharge this, the lithium ions de-intercalate. This is called intercalation. So it's a sandwich compound like this. Graphite sandwich compound, a lot of ceramics are sandwich compounds like this. So the lithiums can go back into this crystal structure over here. But there are different, different types of lithium-ion batteries. Now they're using polymers, and so they can intercalate between layers of polymers and stick a whole bunch of ions in there. This is rechargeable. This is a fuel cell. It's a different kind of battery. It's a battery where you continually add the reactants. And so over here we'd add hydrogen gas at the anode. The hydrogen gas is going to get oxidized to H+, supply electrons to be consumed at the cathode. The cathode, we have air or oxygen. And the oxygen is going to take the electrons. Okay, here they have a continuous flow of salt or electrolyte, potassium hydroxide. So in this particular reaction, at the cathode, reduction occurs, we're consuming. And so the oxygen is pulling the electrons through the circuit. What's it pulling or taking the electrons from? It's taking them from hydrogen. Hydrogen is losing those electrons. Now hydrogen in the presence of base, normally hydrogen gets oxidized to H+, but if we have hydroxide present, the H+ is converted into water. And so this is a combination of redox and acid-base. But they've just shown you the net reaction here. And so this is the oxidation of hydrogen in basic solution. When we add these two equations up, we get this reaction. Hydrogen plus oxygen yields water. The voltage for this is, we look at I'd like to do it this way. I like to write the anode potential first, followed by the cathode potential. Now Petrucci has a reverse because he has a negative sign in there. Because I'd like to just be consistent. The anode's on the left, the cathode's on the right. Electrons flow left to right. And so I would put the hydrogen, and then Petrucci does this weird thing. The couple is hydrogen goes to water, right? But he has it backwards here. He has water goes to hydrogen, and then throws a negative sign in there. And so I would have written this totally different. I would have written this like this. I would have written this one, E naught of the cell is equal to E naught hydrogen goes to water. So it's going to generate electrons. Normally we write hydrogen goes to H+, but H+ is going to be neutralized by the hydroxide, which is going to be converted to water. Plus E naught of the O2 goes to, what does O2 go to? OH minus. So O2 goes to OH minus here. And so I write the anode potential and then the cathode potential. Both of these potentials are very high. The anode potential is plus 0.828 volts. The cathode potential is very high. It's plus 0.401 volts. And so we have a high anode potential, a high cathode potential, which means we're going to have a high cell potential. The cell potential is going to be 1.2 volts. Here. So I don't like to say this because that just confuses things, for what you want for the anode. Let's continue on here. So this is a fuel cell. Fuel cell is going to continue to generate electricity as long as you pump in reactants here. You don't have to worry about recharging this because the only energy storage or electricity storage is just in the potential energies of hydrogen and oxygen. This is a hybrid battery. On one end, we have air pumped in, air pumped out. On the other, we have a fixed amount of aluminum here. And so in this case, we have an aluminum anode, and then our oxidizers are going to be just air, O2 and air, which is free. And so we need some kind of cathode here. The cathode they're using is just carbon. So the electrons are going to come from the aluminum anode to the carbon cathode. From the carbon cathode, they're going to be fed to oxygen here. And so we aren't going to run out of air. We aren't going to run, but eventually we'll run out of aluminum. Once you run out of aluminum, then you're going to get no more voltage, and you'll have to replace this aluminum here to generate electricity. So that's the hybrid. All right, the next topic is going to be corrosion. So we'll take a break and then we'll talk about corrosion. But the batteries, it's just a brief survey. You should know things like, strategies for maintaining a stable voltage. What's the strategy for maintaining a stable voltage? Yeah, and then things like, primary, secondary, fuel cell. This is a general idea, but you don't have to know the specifics of each particular cell.